Good afternoon, ladies and gents, and welcome to this week's Geotalk. It's great to have you all in the audience, those watching on Zoom webinar and those watching live on YouTube. Welcome and thank you for joining us. This week, we welcome Nadja Drabon from Harvard University. She joins us this week to speak about a very interesting topic on the Hadean Eon. And Nadja is currently a postdoctoral researcher at Harvard University in the Department of Earth and Planetary Sciences, and she'll transition to a faculty position there this summer. She completed her PhD and a 2-year postdoc at Stanford University, and as you'll hear today in the talk, her interests really lie in understanding the habitability of early Earth and how it was affected by crustal processes and changing surface environments. So Nadja, thank you so much for joining us. I also want to thank John Hancock's and the CCIC group for sponsoring these Geotalks. And also to let you know that in the next week, we will be transitioning into both talks in person, but still virtual as well. So you can watch both online, or you can come into the Geosciences building and enjoy a drink with us and enjoy the talk in person as well. Of course, all the COVID protocols observed. So without further ado, I'm going to hand over to Nadja. Nadja, you can begin sharing your screen.
All right, yeah, thank you so much.
Great.
Hi, yeah, thank you so much. Thank you everyone for coming. So today I'll be talking about our discovery of a new location with Hadean detritus zircons and what those zircons can tell us about the evolution of the early Earth. So the word Hadean comes from Hades, the Greek god of the underworld, and it's supposed to represent these generally uninhabitable conditions during the early Earth. So initially, Earth was covered by magma ocean and frequently struck by meteorite impacts. Then through 4.6 billion years of history, we start to see the formation of the crust, formation of oceans, the onset of plate tectonics and continent formation to ultimately form Earth as we see it today. So today, Earth is really characterized by this bimodal distribution and surface elevation representing the oceanic crust and the continental crust. And as you all know, life is now really abundant on Earth. So the big question that I'm interested in is, how did we get from this hellish Earth to Earth today? And in my talk today, I'll be addressing two major questions. And the first one is, what was the Hadean Eon like? And because we have very little material preserved from the early Earth, there's a lot of speculation and a lot of different hypotheses that can generally be grouped into two major ones. The first one is the uniformitarian hypothesis. So this one suggests that the Hadean Eon was very much like today, including plate tectonics and the presence of continental crust. And then there's the non-uniformitarian hypothesis. This one suggests that Earth was covered by long-lived protocrust and that plate tectonics were not active. The second question I want to address today is, when was the onset of continent formation and plate tectonics? Many of you have probably seen this graph before. So here we have got age, time, versus the cumulative volume content of continental crust. And you can see that some researchers propose that continental crust started forming really early on and essentially remained constant since then. A number of other models suggest that there was very little continental crust early on, and it really only started forming about 3 billion years ago. So mirroring this controversy is the question of the onset of plate tectonics. And as you're all aware of, Earth is actually the only planet in the solar system with plate tectonics, and we don't know why that is and how it got started. And here again, some models propose that plate tectonics started already in the Hadean, versus others propose that it might have only started about 800 million years ago. So one of the reasons for all of the speculation is that the further we go back in time, the more we lose the rock record. So Archean rocks make up about a third of Earth's history, but actually only 5% of surface outcrop is Archean in age. And then as we go further back in time into the Hadean, we lose the rock record altogether. And the oldest materials are these tiny minerals called zircon. And Zircon is really fantastic because it includes a lot of information. We can date zircons, and it also carries a lot of geochemical and isotopic information that we can use to learn about the early crust. Overall, there's actually only very few zircon locations or locations with Hadean zircons around the globe. So here you can see there's about a dozen or so locations, and most of these have 1, 2, maybe 3 Hadean grains. And the one location that really sticks out is the Jack Hills and Mountain area in Western Australia. So here, extensive sampling efforts have recovered more than 10,000 Hadean zircons. And that is after about 200,000 zircons have been dated. Because of this, a lot of our understanding about the early Earth comes from the Jack Hills. So I'm very excited. We found a number of years ago a new location with Hadean zircons in South Africa, where you guys are all at, in the Barberton Greenstone Belt. And today we found 33 Hadean grains. So to contrast these two locations here in South Africa and Australia, you can see that the Green Sandstone Bed in the Barberton Greenstone Belt was deposited about 3.3 billion years ago, versus the Jack Hills about 3 billion years ago, although there's some uncertainty regarding the actual depositional age. In terms of percentage of Hadean grains, the Green Sandstone Bed, only 0.5% of the dated zircons are Hadean in age, versus the Jack Hills, it's between 2 and 10%. So there's much more Hadean zircon in the Jack Hills and in the Barberton Greenstone Belt. But the Barberton Greenstone Belt location is really unique in that it shows very excellent preservation. So in this photo here, you can see really millimeter scale laminations in these charred rip-up clasts. And that is because the Green Sandstone Bed experienced very early silicification and only lower green schist grade metamorphic grade, versus the Jack Hills, which has been cooked up to amphibulate facies metamorphism. So because of this excellent preservation, we can use the Green Sandstone Bed to test some of the hypotheses that have been put forward based on the zircons from the Jack Hills. And here's just a number of proxies that have been analyzed for the Jack Hills and what they tell us. So they found elevated delta 18O values in the Jack Hills zircons, and this tells us that back then there was already fluids on the surface, so there were likely already oceans. Then the Jack Hills show very low epsilon hafnium values, which is something that can be found in continental crust. They show low crystallization temperatures, which again indicates that there was water present and that the melting conditions were possibly at water saturation. Then the presence of muscovite and quartz inclusions suggests very felsic crust. And the geochemistry of the zircons have been used to determine redox conditions from reduced to oxidized and continental trace elements. And then lastly, they found light delta 13C graphite inclusions, which might be an indication of life. So putting all of this together, Mark Harrison, who's done a lot of pioneering work on the Hadean Eon, he finds that Earth's tectonic regime about 4.3 billion years ago might have been more similar today than previously thought. However, as you can all imagine, with this little evidence from the time period, there's a lot of controversy around these, and a lot of these proxies have been interpreted differently. So, for example, the low epsilon hafnium values have been used to argue for a long-lived mafic protocrust. The low crystallization temperatures do not necessarily indicate water-saturated conditions in arc settings, but could also perhaps form in meteorite impact environments. Then many of the muscovite inclusions have been found to be secondary, and the trace element continental signature is actually non-unique and could also indicate other areas. So today, again, I'll be telling you about the Green Sandstone Bed, looking at these proxies and seeing if these original hypotheses hold up. The Green Sandstone Bed was found in the Barberton Greenstone Belt in the central area here in this highly tectonized area. Here it sits in the uppermost Onverwacht group in the Menden Formation. And the Menden Formation is composed of 5 chromatic flow sequences, each capped by a thin chert layer. So these cherts are chemical and biogenic sediments. And the Green Sandstone Bed was deposited about 3.31 billion years ago. Here's an outcrop photo, and you can see that one of the outcrops of the Green Sandstone Bed is on this ridge right between the Buried Valley and the Stromatolite Valley. In this area of the Barberton Greenstone Belt, many people that have visited the Greenstone Belt have been to this area because it's really famous. So in total, 2 scientific drill cores were taken from Buried Valley, and over 50 publications have dealt with rocks from these 2 areas. So yeah, we are just adding another attraction to this relatively small area. Here you can see the stratigraphy. As I mentioned, the Green Sandstone Bed sits in one of the chert units that caps one of the chromatic flow sequences. The sedimentary unit itself is about 11 meters thick, with the lower 7 meters being composed predominantly of banded chert, some minor tuff, and then the S6 strial layer. So the S6 strial layer was derived by a meteorite impact. What happens is when you have major impacts, the bolide, as well as some of the target rock, vaporize, they form a rock vapor cloud that travels around the globe and rains out in distal areas to form tiny silica droplets. And this is what we find preserved here. Then the green sandstone bed makes up the uppermost 3 to 5 meters of this chert unit. And overall, the preservation, as I mentioned to you, is really excellent. You can see at the base, there's large-scale cross-stratification. As we go higher up, we see fine ripple laminations. And at the very top, we see this beautiful interbedding of carbonaceous chert and the green sandstone bed. The detrital zircon geochronology is shown in this plot here. So you can see the age of the zircon versus the number of zircons of a given age. So you can see that there's a major age cluster about 3.38 billion years ago, and then a smaller cluster about 3.65. Overall, the ages tail off towards older ages. And then here you can see there's a very small cluster of Hadean zircons. However, the detrital zircon geochronology is not consistent throughout the green sandstone bed. You can see that predominantly at the base here, we do see the similar big age peak at 3.38 and then the tailing off in Hadean zircons. But at the very top, we see a young age peak of 3.31, which is with an error of the depositional age. Overall, the zircons are really beautiful and they show oscillatory zoning and sector zoning and cathodoluminescence. And this is really consistent with a primary magmatic origin. So now that I've given you a little bit of background about the green sandstone bed, I'm going to dive into our data. So firstly, I'm going to talk about the nature of the Hadean crust and the crust evolution based on hafnium isotopes, oxygen isotopes, and zircon trace and rare earth elements. And then in the second part, I'm going to digress a little bit and talk about the origin of the green sandstone bed and if there's any chance that we could actually find the Hadean rocks in the Barberton greenstone belt. So I'm going to start off with hafnium isotopes because hafnium isotopes are really well-established proxy of crust mantle differentiation processes. So 176 lutetium decays by beta emission into 176 hafnium, and hafnium in general is more incompatible than lutetium. Zircon is really special again because it includes really high, very high hafnium abundance at the percent level and essentially freezes the signal. So what we measure in the laboratory is the daughter product, so the 176 hafnium over the stable hafnium isotope 177 hafnium, and then we plot it in epsilon hafnium units. So this means that we are basically plotting it relative to Chur, which represents the bulk silicate earth. And because hafnium is more incompatible than lutetium, you can see that the depleted mantle through time tends to develop a more and more positive signal. I'm going to just plot a couple of brains just to tune your eyes in. So the system works in a way that if you have zircons that have values close to 0 or positive, this represents juvenile crust. So that is when magma is removed from the mantle and crystallizes zircon. Once the zircons have formed, they follow this crustal evolution line, and if the material is later remelted, so here about 2 billion years later, you're going to see a very negative signal, so around -20 for very old crust. If this old crust is in a setting where you have, for example, a mantle plume, you're going to see mixing between juvenile and old crust, so you're going to see the spread in values. So this was just to tune your eyes in, and I'm going to zoom into this area here now because we're talking about the early Earth, and here you can see our data. So the data is from both the bottom and the top of the green sandstone bed, so we can see all age clusters. So the first thing you probably noticed that prior to 3.8, most of the zircons really plot below Chur, and they fall in this really general, very broad crustal evolution trend, and indicates that magma was derived from the mantle about 4.2 to 4.5 billion years ago. Throughout this time, we don't see a clear evidence for juvenile additions, so very little evidence for derivation from a Chur reservoir or even positive mantle reservoir. In general, sometimes using hafnium isotopes, it's possible to deduce the original composition of the crust. based on the slope of the array. However, as you can see, the trend is really broad, and it's both consistent with mafic crust and TTG-like crust. And this really makes sense because if you derive crust originally from the mantle and then you continuously remelt it internally, you're going to get increasingly more felsic compositions. However, there's one grain that plots pretty far below relatively negative values. And this one only really makes sense if it was derived from really felsic crust, because otherwise the crust would have been derived from the mantle prior to the formation of the Earth, which is not possible. Then at about 3.8 billion years ago, the signal really dramatically changes. So around this time is when we start losing evidence for this really long-lived Hadean crust, and we start seeing really abundant juvenile additions. So after this time, there's an almost complete loss of the Hadean crust, and this old crust was really destabilized, and we see the juvenile additions, but also some mixing with older crust, but that older crust was likely not Hadean in age. So overall, this is really interesting because we have got this long-lived protocrust that was stable for several hundreds of millions of years and only experienced internal remelting, but no juvenile additions. And then after 3.8, we see evidence for crustal destabilization and frequent juvenile additions and recycling of older crust. Next, I'm going to talk about trace and rare earth elements in zircon. And trace and rare earth elements have been really frequently used for a long time. And that is because trace element composition reflects elementally partitioned composition of the source magma at zircon saturation. And different compositions of the zircons are really a reflection of the original melt composition, mineral assemblage, temperature, and also other things like pressure. So as I said, it's been used for a really long time, but it was only in 2015 that Craig Grimes published a study in which he compared the composition of igneous zircons from different tectonomagmatic terrains. So his goal was to see, okay, if we look at all of the zircon geochemistry, and zircon geochemistry tends to be really valuable, even for a single pluton. But he was testing, okay, if you look at certain trace element proxies, can we distinguish these different environments? And he found that he can use uranium, niobium, scandium, ytterbium, gadolinium, and cerium to really distinguish between these different settings. So the settings that he studied are just very broadly the relatively undepleted mantle. So as we see today in Iceland or Hawaii, then depleted mantle setting as we see in today's mid-oceanic wedges, and then arc settings, modern arc settings. But before I move on, I just want to mention that for the Archean, there's alternative tectonic processes that have been proposed. So here we see a model for plate tectonics. And the early Earth, there might have been drip tectonics, where there was gravitational overturn of the crust. And because this is just a model and there's no modern example, we are not quite sure what the geochemical signature would look like. And there's a possibility that it might show a similar signature to arc environments. So here are results from the trace element study. So firstly, let's look at the uranium over ytterbium versus hafnium plot. And I'm showing here zircons older than 3.8 in these red colors, and then younger than 3.8 in these blue colors. So overall, firstly, you can see that there's quite a bit of variability also for the old zircons, again, speaking towards the heterogeneity of the old crust. And you can see that all of these zircons plot in the field for continental and relatively undepleted mantle sources, and we do not have any good evidence for a source from a depleted mantle origin. So the next diagram here, uranium over ytterbium versus niobium over ytterbium, is really similar to the Pierce diagram, and it's basically tracking the niobium depletion that is so typical for modern continental or oceanic arcs. And the first thing you noticed here probably is that these warm color zircons, so the zircons older than 3.8, almost exclusively plot in the field for the relatively undepleted mantle. Then zircons younger than 3.8 either plot in the arc field or they kind of plot along the boundary between the two fields. And could this represent either a relatively undepleted mantle field or an arc field, or it could indicate that you have a plume, for example, hitting a continent. And then lastly, we are looking at the scandium over ytterbium proxy. And this one is a little bit counterintuitive because scandium is not usually expected to be high in arc settings. But the reason that mantle settings have relatively low scandium is that when you produce melts there and you want to crystallize zircon, the melts must have undergone really extensive fractionation before they reach zircon saturation. So by then, a lot of the scandium has been removed from the melt. And then here again, we see that the zircons, the old zircons, older than 3.8, plot in the relatively undepleted mantle field versus the younger zircons, either plot in the arc field or in the transitional zone here. So I did this with these proxies, but then also with the other ones that I was mentioning earlier, and I'm getting a really consistent picture that the old zircons show this relatively undepleted mantle signature. But of course, it's never that straightforward. So here I'm looking at the temperatures that we calculated based on titanium and zircon. And you can see for the Hadean grains overall, there's quite a bit of spread, again, supporting this heterogeneity of the early crust. But what is really noticeable is that the zircons overlap really well with the continental arc zircons, but they look fairly different to what we find in mantle settings. So the undepleted mantle usually has a higher temperature zircons. So why is that the case? How can we explain this? So I was doing a little bit of work with Brennan Keller at Dartmouth University, and he's this really fantastic database in which he looked at 40,000 whole rock samples throughout Earth history. And he found that there's changes in the geochemistry because of the higher heat flux from the mantle during the early Earth. So what you can see here is that this also affected the zirconium concentration in the melts. You can see that they were quite a bit lower during the early Earth. And this lower zirconium concentration is going to affect when the magmas reach zirconium saturation in order to crystallize zircon. So by the Paleoarchean, the temperature probably was about 35 degrees lower, and you can continue extrapolating that into the Hadean, so it must have been quite a bit lower then too. So based on this, if we shift this by about 35 degrees Celsius, we can see a better overlap with the undepleted mantle sources, but quite a few of the zircons still show relatively low titanium values. And this would be in agreement with some form of hydrosmelting, so that there was some melting involved in forming these zircons, but that this melting based on the other geochemical signatures did not reach the characteristics of modern oceanic and continental arcs. So next I'm going to talk about oxygen isotope geochemistry because they also confirmed that there was some water present. So oxygen isotopes are sensitive, temperature-dependent tracers of fluid-solid interactions. The mantle itself has a very consistent value of about 5.3 per mole. So if you look at oceanic crust, especially the upper oceanic crust, you have values higher than 5.3. And this is because the melts from which these zircons formed incorporated crust that has undergone low temperature alteration prior to melting. So that is what drives the values higher. Versus the lower oceanic crust is going to show lower values than 5.3 because here the melts incorporated crust that had high temperature interactions with fluids. Overall, continental crust tends to have higher values, about 8 to 10. And when we look at sedimentary rocks, these are the ones that have really extremely high values that can be up to plus 40 per mole. Overall, as I mentioned, oxygen isotopes, because of this, are really great at tracing the influence of fluids, but they are a less powerful proxy when it comes to distinguishing different tectonic magmatic domains, unless there was a big change in how much sediment was incorporated. So here are the results from our oxygen isotope study. And you can see here for the Hadean zircons that there's quite a few that plot on the mantle line. And then there's a number that plot higher, again, supporting the notion that there was already water present on the Earth's crust. But overall, you can see there's a lot of variability, and this really indicates that prior to 3.5, there was reworking of a diverse assemblage of rocks with diverse delta 18O values. Younger than 3.5, we do start seeing more clustering, and we interpret this to reflect more distinct, perhaps localized sources. So here I'm putting all of this together, and altogether the evidence suggests that the Hadean crust and the source to the Green Sandstone Bed was characterized by relatively long-lived protocrust that remained stable until about 3.8 billion years ago, so for several hundreds of millions of years. and that this crust was originally derived from a relatively undepleted mantle, but then experienced internal remelting, causing the crust to become heterogeneous. And we also find evidence that this remelting incorporated some amount of liquid water. Then after 3.8 billion years ago, we see more juvenile additions and more common arc-like hydrosmelting signatures. And also the loss of the Hadean crust. But in the end, we're only talking about the hinterland to the Green Sandstone Bed. So the question is, could this be a global signal? And before I move on and compare this to a couple of other areas with Paleoarchean and sometimes Hadean zircons, I just want to caution everyone, because there's so little material preserved from the early times that it's very difficult to really deduce, okay, is this a global signature or not? But there are some very curious similarities. So here I'm showing the epsilon hafnium signature for different Archean cratons. And most notably, you all know the Zircon craton that incorporates the Jack Hills. So probably one of the first things you notice is that, especially prior to 3.8, we see few zircons that plot on Chur, and a lot of them have fairly negative values. And a lot of these also show these general crustal evolution trends. And these arrows that are drawn in here, those are not my own. So these are from people that have actually studied the areas in great detail and found that, again, here we see these crust evolution trends and some evidence for long-lived protocrust. Then Annie Bauer published a manuscript last year, and she did a change point analysis to see, okay, at what point in time do we start seeing the shift to higher epsilon hafnium values that indicate juvenile additions? And she looked at these areas, but then also other areas around the globe. And she found that there's, in general, the shift between about 3.8 to 3.6 billion years ago. And they hence proposed that the secular shift in the global hafnium isotope record reflects a gradual yet widespread transition from stagnant lid to mobile lid tectonics on the early Earth. And you can see here, putting on top of this, our results from the Green Sandstone Bed. This seems to overlap the story, what we see, pretty nicely. So here's a different way of looking at it. So here I'm just plotting everything together. But doing that, I want to point out that, of course, this is going to be biased for the older zircons towards the Jack Hills, for which we have the most data. But you can, again, see very nicely that prior to 3.8, we see a lot of negative epsilon hafnium values. And then starting at 3.8, we see that there's more frequently juvenile additions, and we start the formation of this string of high density epsilon hafnium clusters, indicating juvenile additions. So this all makes sense, but what about the trace elements? Do we see something similar there in other areas? And there's not been much data published, but here I'm plotting the few data points from the Jack Hills and the Shingbom Craton zircons. And you can see overall that prior to 3.8, most of these zircons really, again, have this mantle signature or plot in the transitional zone, where they could either be an arc signature or a mantle signature. But only very few zircons have a very clear arc signature. Then at 3.8, this is really when we do start seeing this hydrosmelting signature become much more common. So again, we have to be careful because there's very little material left from that time period. But the similarities between these different areas are really striking, and they apparently support the case for non-uniformitarian Hadean Eon and widespread crustal destabilization and onset of common hydrosmelting, which is a sign for mobile tectonics and could quite possibly be a sign for plate tectonics in the 3.8 to 3.6 GA time window. So next, I'm going to digress a little bit and talk about the provenance of the Green Sandstone Bed. So where's the source of the Green Sandstone Bed? And is there any chance that we might find Hadean rocks in the Barrington Greenstone Belt? And I can already straight up tell you that probably we will not be able to find the Hadean rocks in the Barrington Greenstone Belt. So here I'm looking at the Zircon geochronology of the Green Sandstone Bed and comparing it to potential sources and the detrital zircons in the Barrington Greenstone Belt. So you can see here the green sandstone bed with a major age peak at 3.8. And you can see that felsic, barberine, igneous rocks usually do not show that age. There are several episodes of predominant felsic volcanism, but they do not overlap with this major age cluster or the older, smaller age cluster. And it's very similar with the detrital from the Barberton Greenstone belt. So these zircons here, it's almost 7,000 zircons from 112 samples across the entire Barberton Greenstone belt and the entire stratigraphy of the Barberton Greenstone belt. And we do see nice age clusters that mostly overlap with the felsic igneous rocks in the Greenstone belt, besides this age cluster here. But again, it's really interesting that the major age peak of the green sandstone bed falls right into this trough here. And then overall, also very importantly, the zircons, these old zircons that we find in the green sandstone bed, we do not see otherwise in the Barberton Greenstone belt. So there's no evidence for GSB crust in the Greenstone belt. Another piece of evidence for the origin of the green sandstone bed comes from the zircon morphology. And while a few zircons still show some straight crystal faces, there's a number of zircons that really show like exceptional rounding. And this is something that I have never seen before. And also talking to other people that do a lot of work on zircons, seeing zircons this round is really rare and indicates really long distance transport and potentially transport in a way that really efficiently rounds zircons. And one potential way to do that is through aeolian transport. Looking at the chromium spinouts, the chromites, we get a very similar story. So Ben Byerly here analyzed the chrome number of the spinout. So that's a chromium aluminum ratio, which is really a fingerprint of the chromatic flow sequence from which the chromites are coming from. And he found for the green sandstone bed a major age peak at about 81, 82, and then a few smaller peaks. So comparing this to major flow sequences in the Barberton Greenstone belt, we can see again that this major chrome number peak does not occur in any of the analyzed chromatic rocks that Ben looked at. For the smaller peaks, there might be some overlap, but this major one, again, there's no similarity here. And the chromium spinouts, many of them also really show this exceptional rounding, again, speaking for relatively long distance transport. Another piece of information here is that the green sandstone bed is already unusual not only in its composition, but also just itself in its presence. So I mentioned to you that the green sandstone bed sits in the Menden Formation, and the Menden Formation is really this underwater world where we have extrusion of chromatic flow rock and deposition of chemical and biogenic sediments. But we see very, very little evidence for any siliciclastic, so little evidence for exposed topography and erosion. But then all of a sudden we have the green sandstone bed, which is a siliciclastic bed. And then the last piece of evidence for the origin of the green sandstone bed comes from the sedimentology and stratigraphy itself. So I mentioned to you these beautiful sedimentary structures, and overall we see this great decline in current energy from large-scale cross-stratification to small ripples and these charred rip-up clasts. And here at the very top, we see this interbedding of the green sandstone bed with carbonaceous chert. And carbonaceous cherts are composed of organic material, and for those to really settle and be deposited, you essentially need to shut off current energy because the organic material is so light. If you have currents, it's going to be just swept up again. So this means that we have relatively high current energies and then a pause in currents. And this type of heterolithic strata is very typical for tidal environments. So we believe that the green sandstone bed was deposited in a shallow marine environment. And you can also see here that there's an erosional unconformity at the base. And this becomes a little bit clearer when we look at the map view. So this is a map that my PhD advisor, Don Lowe, created. And you can see here, it's a relatively small scale. So this is only 4 meters. And you can see the chromatite in purple, below and above, and then in gray, the black and white banded chert, the stria layer, tuff, and then the green sandstone bed itself. So you can see that prior to deposition of the green sandstone bed, there was some faulting and block rotation going on. And then there was a period of erosion and the green sandstone bed was deposited. And here's just a photo from outcrop where you see this erosional unconformity at the base. So to make this happen, clearly there must have been some form of exposure and erosion. So there must have been some terrestrial conditions that allowed for that. And then lastly, I just want to point your attention again to the meteorite impact layer that is clearly very closely associated with the green sandstone bed, but not. But it seems like there was some time between the deposition of the sphere layer and the deposition of the green sandstone bed. However, this S6 meteorite impact was a really major one. So you can see here these spherules that I was explaining to you earlier from the rain out from the rock vapor cloud. And the S6 sphere layer is about 15 centimeters thick. And this, just in contrast, you all know the KT impact that killed off the dinosaurs. And that one also has a sphere layer. But in distal locations, that sphere layer is only between 3 millimeters and perhaps a centimeter thick, versus the S6 impact sphere layer is 15 centimeters thick. So it was a really major impact event. And although it did not immediately precede the deposition of the green sandstone bed, some of the green sandstone bed from the source must have been associated with the impact, because we find quartz grains with planar deformation features, which are an indication of deformation because of the impact in the target. So putting all of this together, the origin from outside of the Barberton greenstone belt and long distance transport, the deposition, at an erosional surface. So we are probably in a shallow mean environment, really closely associated with the terrestrial environment. This intense drowning that could potentially be explained by aeolian transport, because again, that is the most effective mechanism of drowning grains, and the evidence for some of the target rock within the green sandstone bed from the meteorite impact. This is our current working hypotheses for the origin of the green sandstone bed. So we believe that the S6 meteorite impact hit and that was fairly far away, so we do not see any direct impact ejecta, but that this impact caused uplift and exposure and derived from which the green sandstone bed was derived. Then this material was transported for fairly long distances, so tens to hundreds of kilometers, and that possibly through aeolian mechanisms, just to explain this exceptional rounding. And then the sediments were redeposited and resedimented in a tidal environment. So overall, as I already was mentioning earlier, we believe that there's very little chance that we can actually find the Hadean source rocks within the Barberton greenstone belt, because it seems like the material was transported from fairly far away. Just to finish off, here just a couple of take-home messages that I hope you all take away from this. And that's firstly that you guys in South Africa have this really interesting sedimentary unit that shows evidence for lost source terrain that recorded 800 million years of Earth's history. And we find in those zircons evidence for long-lived protocrusts that formed in the Hadean and was derived from a relatively undepleted mantle, and that there was a major crustal transition that occurred about 3.8 billion years ago. And we do not only find evidence for this transition in the green sandstone bed, but also in other areas around the globe, possibly speaking towards really a global change in the tectonic regime. And then lastly, the sediments of the green sandstone bed were derived likely from long-distance transport from outside the Barberton greenstone belt. So with that, I'm going to just leave the slide up here and then take your questions. Thank you very much.
Nadja, thank you so much. That was a really, really fascinating and thought-provoking talk. So thank you so much. And that is also testified by the audience. 30 people watching on Zoom and several on YouTube. So thank you all for joining us. And if anyone has any questions for Nadja, please, you can ask questions in two ways. You can either ask a question in the Q&A box, type it in, or you can simply raise your hand and we'll allow you to speak. So we have the first question from Lou Ashwell, who asks, what motivated you to look for zircons in the green sandstones?
Yeah, so what motivated us my one collaborator, Gary Bailey, he actually analyzed the green sandstone bed, I think about 15 years ago for the first time. And he found this big H cluster at 3.4. and then some older zircons as old as 3.8, but he at that point did not find any Hadean grains. And then when I came along during my PhD, one of the studies I did, and I didn't talk about, is I took detritus zircon samples from all across the Green Sandstone Bed, and that really showed me this very, like, almost boring signature where we only have the same. Let me just go back to the slide. Where we have the same zircon age clusters over and over again, but with different abundance or different heights of the clusters. And this one sample that Gary Byerly analyzed 15 years ago really stuck out. So then I suggested basically, okay, this bed is so different. We see all these old zircons. We should just really go in and analyze, a few hundreds, maybe even thousands of zircons to see if we find anything older. And when we did that, that's when we found the Hadean zircons.
Okay, thank you, Lou. We have a question from Dave C. We found rounded detrital zircons in an alkaline intrusion in Sweden. Could these thus not come from below as opposed to being transported?
Yeah, that's a good question. I'd be interested maybe if you could talk about your discovery of the rounded zircons a little bit more in Sweden, like what the setting was. I'd be really curious to hear about that.
Yeah, Dave, if you just, I'll find you in the list and I'll allow you to talk. It'll be great to hear more about that. That sounds very interesting. I'm allowing you to talk, and you just need to unmute if you wish to talk.
Okay, can you hear me?
Yes, we can. Thank you so much.
Yeah, this is the Norra Kärr per alkaline intrusion in Sweden, which is a rare earth deposit. And we just sampled some of the stuff in the margin, and there were a lot of these rounded zircons in it, which obviously don't belong to the alkaline intrusion, but must have come from further down, and they're also a lot older than the Norra Kärr intrusion, which is about 1200 million years old. So it seemed to us that what had happened was that these zircons had got taken up as xenocrysts, and because of the sort of rapid movement of the intrusion upwards, these zircons had become rounded. Okay.
Okay, yeah, no, that's really interesting. You have to think about that a little bit more. So in general, there's also a different setting that might produce rounded zircons, and that's metamorphic zircon can be rounded. But when we look at the CL response and the zonations, we don't, and the geochemistry, we don't find evidence that could have caused that the zircons could be metamorphic in origin. But yeah, that's a really interesting thought. I have to think about that a little bit more. It seems like that could be a possibility.
All right. Do we have any other questions? Whilst people are thinking of questions, I've got a question, Nadja. It relates a bit to the rounding of the zircons. And I remember a paper several years ago by Balz-Camber talking about the generation of Hadean zircons in impactors. And I can't remember right now all the details of the evidence he used, but it struck me that the relationship between that impact and the Green Sandstone Bed, I guess Balz-Camber would say, might be evidence that some of these zircons are being generated by impacts. And maybe have you thought about that hypothesis, and maybe you have some evidence to disprove that?
Yeah, so it is a possibility. So the zircons formed in impact melt sheets can also have really low titanium values, which really would be in line with what we see in some of these really old zircons. So it is a possibility, and I really try to stay away from speculating about what caused the melting, the internal remelting of this long-lived protocrust, because we really don't know. So it could be meteorite impacts, it could be volcanic resurfacing. In general, just like one thing I want to point out is that we have not found a zircon yet with shock features that would indicate derivation from an impact crater. So it seems like there must have been uplifted material, but not from the actual crater itself.
Okay, thank you. That's fantastic. Very interesting. Are there any other questions from the audience? Feel free to raise your hand or just type them into the Q&A box. All right, well, I don't see any other questions right now. So for a moment, what I'm going to do is share my screen. And I'm just going to remind everyone about Geotalk next week, which takes us to a very different period in Earth's history. And the talk next week, if I get to the right slide, is by Pia Viglietti from the Field Museum of Natural History in Chicago, and she's speaking about evidence from South Africa for a protracted end Permian extinction on land. So a very different time period, but should be equally interesting. All right, so that's next week's talk. I've got one last question, Nadja, if you have some time to answer this one. This is from Toriso, who asks, are there any zircons anywhere in the world maybe exhibiting similar characteristics to those of the Green Sandstone Belt that could assist in tracing back the source? Toriso is an MSc student from Wits.
Yeah, that's a really great question. So as I was showing, there's a lot of similarities between other areas with the old zircons. So there tends to be, the subchondritic epsilon hafnium values and these that follow these crust evolution lines. And then it seems, at least from the published data, that in terms of geochemistry, there might also be a similar origin. So that might indicate that the nature of the early crust was similar in many areas. But then the zircon age peaks can be quite different. And what is really curious that when we look at the age distribution from the Green Sandstone Bed and compare that to the Jack Hills, they're actually exceptionally similar. So the age classes overlap really nicely with an error. So it is possible that those had a similar source.
Okay, well, thank you so much, everyone. And Nadja, thank you once again for a really, really thought-provoking talk.